Can you hear me? Everything's fine? Okay. This is my presentation for this year's conference. It's a presentation called Implementing Netclass to Netclass Constraints Using Custom DRCs. It's a privilege for me to be here. I've wanted to make a presentation for several years. And I also wanted to be able to actually do netclass to netclass constraints. So this is an opportunity for me to solve both problems at the same time. I've taken inspirations from Seth's presentation a few years ago, which was like level up your custom DRCs. And I wanted to take that knowledge and that presentation and then incorporate it here to solve a very specific problem within netclass constraints. But let's get to it. First, an introduction to myself. I have a master's degree in electronic engineering from 2005, so about 20 years of experience. I work mostly in telecom industries and high reliability industries, mostly doing power supplies within those industries, but all in all, a very good experience of both digital and analog electronics. The last 8 years, I've been working as a freelancer, so had a lot of different companies as customers. I've mostly been on site at their place to do the designs and the development, but I also have my own lab where I can do anything from DC to 20 gigahertz. I've been a KiCAD user since 2014, I believe, version 3, I believe it was. So it's been many years. I don't have a family, but as you can see in the picture, I have a lot of babies in my lab. So electronics is really very much a part of my life. So small disclaimer: I'm going to do some presentation that involves high voltage design, but I'm not here to teach you about high voltage design. So if you want to directly copy any of the high voltage stuff, don't kill yourself. I don't take any blame for accidents that happen because of that. Just letting you know. The presentation itself, I will start off by doing some introduction to what is constraints. I assume that most of you have a pretty good idea of basic constraints, but I'm going to cover it anyway, just to, go through the explanation of what we're doing. And then I will try to do an explanation of specifically what is netclass and netclass constraint compared to regular constraints. And then we're going to dive in the actual design of an offline converter. I'm not going to spend too much time on how to design an offline converter, but more like taking the offline converter as an example of how to use netclass to netclass constraint, because an offline converter is a perfect example of explaining exactly that. And then, of course, we're going to finish off with some Q&A. If something goes, if I say something that you totally do not understand, then raise your hands and I will try to explain a little bit better. But other than that, I think I will do like small question or ask for any questions during the course if we're in a topic where it gets a little tricky to understand. So you get a chance to say, hey, can you explain that a little bit better or something like that. Okay, let's go. So what are constraints? Well, constraints are limitations that monitors and controls are designed. It's basically putting on the limitations like physical, mechanical, electrical constraints into our designs, so it limits what we can do. So under normal circumstances, we don't do any mistakes. That's the basic of it. Let's take an example. If you're putting a constraint into your design that all traces should have a minimum width of at least 100 micrometers, that's a constraint. There could be different reasons for that. One typical reason for having such a constraint is that you're able to manufacture it. The same can be said for like a trace-to-trace clearance. There could be many reasons why you want clearances between two traces. And one of them could be that you're actually able to manufacture them without them accidentally shorting to each other. So that's another simple example. We will come back to some more examples later. So why are constraints important? As I just mentioned, ensure manufacturability of our design is probably the one that most of you encounter when you're doing design. You go into probably a web page, you order a design, and you'll fill in like the some of the tiniest dimension of pieces in your board. And that's actually constraints that you then have in your design, such that the manufacturer can come back and say, hey, we can actually produce this for you. Because you don't want, a week after you order the design that they say, hey, we can't actually produce it. That's very costly. You just spend a week finding out that it was no good. Or even worse, it might come back after a week and you get it in your hands and you say, hey, that's not really what I ordered because you didn't comply to the limitations of the manufacturer. So that's a very good reason why you put in constraints in your design. Then there's something like electrical integrity that, your board will work. Let's say you're very creative and you just draw the lines all over the place. Some lines will short, nets will short. There's a good chance your board will not work at all, right? So it's good to have those kind of constraints into your CAD system. You take it for granted, but you could do electrical design in Microsoft Paint, right? But it will not tell you that you're shorting the designs. But you put in the constraints that, hey, net should not be shorted, and it will come back and tell you, hey, you've done a mistake here. And that ensures the electrical integrity. Another thing is if you have like quality measures or quality regulations that you want to comply to. That's often if you have customers, let's say your customers in the aviation industry or in automotive industry or medical industry, they might have a set of constraints. They come back to you and say, hey, you need to comply to these constraints. It might not have anything to do if your design will work or not, but they say, we'll need you to comply to these constraints, otherwise they don't live up to the quality requirements we have in our industry. So you put these constraints into your design in order to be able to sell your design to these customers. And an extension of that is safety regulations, where you need to make sure that your design is not dangerous to the people using it, or it will not become dangerous because it's in an environment where it can cause a dangerous situation. A good case of that would be like high voltage systems, that you don't want anybody to touch them, or you don't want accidental electrical bridging within your design. And then you can use constraints to ensure that when you're doing your design. Another reason why it's important is that you can optimize performance. If you type in the actual limitations of your manufacturer, you're able to squeeze in an easier fashion your design into a very small real estate, where you normally might have to sit and gauge with your eyes, is this close enough, and pull things apart. You can just have your management system within your CAD system tell you, hey, you're not complying to your constraint. There's an error, take things apart, and then your design is automatically ensured to be as small as possible. That's an example of optimizing the real estate of your design. And another thing, which is maybe not mentioned as much, is if you're working in larger department or larger project with many people on them, you often don't want like one person using one set of rules and then another person using another set of rules. You actually want to put in all your constraints into your CAD system, and then having the management of the constraints be within the system itself, such that multiple people working on the same project does not follow completely different rules. I mean, there's a saying that a lot of quality comes from the consensus within a team to do it the same way. Not that there's necessarily a quality limit to what is good and what is bad, but that you agree upon what it is. And a good place to have those constraints is within your system. So those are examples of why constraints are important. Where do we normally put constraints into our system? So I take a very rudimentary design flow here. Usually it goes something like, you do a business case, you do a product specification, you do a design, you do some manufacturing, and then you make money. Everybody's happy, right? And in the design phase, you do something like simulations, maybe some calculations, stuff like that. You go to do the schematics, then you do the layout. And your constraints fit somewhere in here. So constraints will limit how you do the layout. But in many cases, when you set it up, you take your schematics as a starting point, because the schematics have the functionality of your design. You can look at the nets and easily say, hey, what is this part actually doing in the design? And should we have some constraints on these nets or these groups of nets or this group of the system in order to make it work correctly? So let's take a few examples here, just in order to make it completely sure that you understand what constraints is. We already talked about like minimum trace width. So how wide can a trace width be? And if you make a trace that is smaller than that, you will get a constraint violation. That would be one example. We have like a minimum hole size. That's a constraint that you usually have in your design. You have a minimum solder mask sliver. If you have two solder mask opening, how small can the sliver between those openings be? That's a constraint you put into your design. And hole-to-hole spacing. These are all related, or mostly related to if you're manufacturing design, will your manufacturer be able to actually produce your PCB? You can have something like, the total trace length of a trace. If you have critical timing in your design, then you might need to know exactly how long is it, or does it meet those timing requirements, and does it meet those length requirements? That's a constraint you can have in your design. Length matching between several traces in design is an example of a constraint you can have, where you say signals coming from one source and arriving at another have to arrive at the same time. You put that constraint in your design, and thereby you're constraining the length of those traces in order to meet that requirement. And then we have the net clearance, where, as in the example here, you have like a via and a trace, and what should the clearance between those two nets be? You can have a general constraint saying what can a clearance between two nets be, but you could also, let's say, the via is in one net class and the trace is in another net class. Is there a specific requirement to the clearance for those two nets to have? Let's say there's noise in one of the signals and you don't want that noise to contribute to anything in the other signal. Well, then you might want to add the clearance between those signals to avoid that. That's constraints in general. So what is the difference between that and net class to net class constraints? Let's take the example we have on the board right now. Let's say you have a design, you have some different types of nets in your design. You have a ground net, you have a switching node, you have a sense signal, you have a high voltage signal, and then you have some high frequency signal, maybe a differential line with those high frequency signals in there. So how would you go about, saying what constraints do we need? Let's take the ground node. A ground node does typically not have any constraints. You're not really concerned about it. It is by definition not carrying any voltage, not carrying any, it is carrying current. But it's also very immune, it should be. In most cases, you probably have multiple layers of complete ground, and it's pretty robust. There's not going to be any interference with your ground. So you could probably do with a very small clearance, so basically any other signal. Then you have something like a switching node, which usually have very high transitions of voltage and current, and thereby causing a lot of crosstalk and noise and other signals. So you kind of want large clearances to other signals in that type of net. A sense signal is a good example of a sensitive net that you kind of want clearance to other signals that can cause interference with it. The high voltage is an example of something where if the voltage is high enough, it can cause bridging. So maybe you want a specific clearance in that net to other nets as well. And the high frequency signal is kind of like the sense net. Typically a sensitive net, because if you're carrying high frequency information, you're probably not having a lot of energy to carry that information, and any energy interfering with that signal can cause loss of information, thereby loss of transmission. So you normally want large clearances for that type of net as well. So with the generic clearance approach, you just set up one parameter that dictates what should it be. And let's say all your ground or DC voltage is in one net class, your switching node is in another class. You can just set the parameter large enough to accommodate all needs. Does that make sense? Well, let's say the ground node, you just set it for a small clearance because you don't need any clearance. For the switching nodes, you set a very large clearance because, hey, then you're sure that every other signal will have a large clearance to the switching node, and you're good, right? And you can do the same for the sense node and for the high frequency stuff. But as we just mentioned, the switching node does not need a high clearance to ground, for instance. But if you set a high clearance for the switching node, you're utilizing real estate on your board unnecessarily. There might be a few nets actually in this net class with the switching node that has the same type of voltage, same type of current, and thereby not needing a big clearance to each other. So you might want to group them and actually have a small clearance within that net class, but to certain other net classes, you want a large clearance. Maybe you still want a small clearance to ground, but a large clearance to the sense net. And KiCAD in its, how do you say, when you download it, there's no way to go in there and just type that in and say, this is how I want it. But that's the essence of the net class to net class constraint. And now I'm going to ask you if what I'm saying makes sense, because this is very relevant to what we're trying to do. Are there anyone that needs further explanation? Any more examples? Just raise your hands. Okay, that's great, because this is the problem we're trying to solve here. We're trying to say, let's say all our switching nodes is in one net class. How do we differentiate between clearances between other net classes such that it's not the same clearance everywhere? As I mentioned, you can enter the board setup, you can type constraints, and you'll have a set of constraints. These are typically related to the manufacturing. You can you can click on the net classes, and there you can create some net classes, and there you can create global clearances for those net classes. Everything's good, but that's going to be like the largest common denominator I just mentioned, like the large net class that will cover everything. And then if you want the black magic fun time, you'll have to go into the custom rules and create something that is unique for what you're trying to do. And this is what we're trying to set up here. Okay, the offline converter design. This is a flyback converter. I'm not sure how many of you are feeling good and well about an offline flyback converter design, or is there any of you that would feel, okay, I could use a little explanation of what's going on in such a design? Okay, that's great, that's great. So I started out by mentioning that it's a very good design for having these net class to net class constraints, because I'm not sure if you can see my mouse pointer. I hope you can. So here on the left side, it says primary. So you have a primary side over here, and then you have a secondary side over here on the right side. And then there's an isolation barrier in between. So you're basically taking 220 volts in to the design. You're rectifying it, creating a rectified voltage. Some of that is feed down to drive a switch mode regulator. It has an integrated MOSFET, and that drives a transformer that converts the voltage to the secondary side, where you create a low voltage. And then you need a large voltage clearance between the primary and the secondary side in order to create a safety for your 220 volts electronics, not to migrate into the low voltage electron on the secondary side that is usually connected to any user devices. So for safety reason, by law, you typically need a certain isolation barrier. And let's say we put this isolation barrier at created a very large clearance as an isolation barrier and just said, okay, everything on the secondary side would just create a huge clearance for those signals. Then they would also need a huge clearance to each other, which would make the secondary side huge. And you don't really want that, because there's no requirement for them in between each other to have a large clearance. They can just use the generic minimum clearance that is common for your manufacturer, but you still want a large clearance to all the things on the primary side. And the same thing can kind of be said for some of the high voltage stuff. You have a positive and a negative. I mean, they're exchangeable, but your 220 volt line, or 110 if you're in North America, and if you're in other parts of the world, I don't know what you're using, but you'll use some version of a high voltage. You'll see that some of the nets here, where's my mouse again? Here. Some of the nets here actually do not have a big voltage difference in between them. Like there's a 10 ohm resistor here, that it will not create a large voltage across that 10 ohm resistor, but it's residing at 220 volts. So you don't want a large clearance on those two nets, but you probably want a large clearance on every other net. So it's a good example of why we need to differentiate the clearances in the design. So how do you go about this? And that's the procedure that I'm going to explain to you now. At least this is how I did it. I cannot say if there's 100 other ways to do it. And if you have some good suggestion at some point, maybe during the Q&A, you can come in with your suggestion or corrections if I do something that is completely wrong. But so here's my take on it. This is how I did it for this design. So first, we try to identify what are the actual net classes that we want in our design. you kind of pick them out and you say, okay, this is a net class, this is a net class, and this is a net class. And these are the ones that I came up with. So there's the positive input voltage, there's the negative input voltage, there's the rectified input voltage, there's the switched input voltage, and because in a flyback converter you're actually seeing a reflected voltage from the secondary side onto the primary side, there's a good chance you're seeing a much larger voltage on that net compared to the other nets in the design. So we're putting this in a separate net class of its own. And maybe a little hard to see on the screen, but the green wires down here is what I call the primary side voltages. Those are low voltages compared to the primary ground. So they're in the net class by themselves. And then we have the secondary side net class, which is all the signals on the secondary side, which we already said are all low voltages, but need a large clearance to everything on the primary side. So now we identified it. We said, okay, there's 6 net classes. It's not an exclamation mark on the right side. It's where the isolation barrier is going. Just letting you know. So here's is how I did it. Just for visualization, I take those net classes and I put them into a spreadsheet. I give them some kind of name so I can recognize them. I put all 6 net classes here, and then all 6 net classes here. It's the same net classes, but put them in the rows and put them in the columns. And then, of course, I will do the correlation between the clearances that are needed between the net classes down in the actual field. And only half of them are going to be filled out, because otherwise I was just putting in the same information twice. So let's look at the examples here. Primary to primary clearance. So that's within the net class itself. I put that at 150 micrometers. That's just the limitation of whatever manufacturer I decided to use. Secondary to primary. Remember, we're not talking about secondary voltage in general and primary voltage in general. We're talking about the net class secondary to the net class primary. Those are 2 net classes. I set that to 5 millimeters. Again, if you're doing high voltage design, you better consult somebody who knows what they're doing and ask for your numbers to your design. Don't take my numbers for it. This is just something that could be totally made up. Don't kill yourself. Huh? Well, I think that's irrelevant for this particular. As I said, we're not talking about the actual high voltage design here. We're just talking about the concept of a voltage barrier or an isolation barrier between the primary and secondary side. So I set that to 5 millimeters. And the secondary to secondary, that is signals within the secondary net class, I set that to 150 micrometers. And for the switching node on the primary side, to the primary voltages, and again, primary is the net class called primary, I set them to 2.5 millimeters, and so on and so forth. We fill in all what we find relevant. We got some numbers down here. And when I've done that, then I have the numbers that are relevant to move forward with the design. And then we're preparing the setup. We create the net classes. The net classes can be created both in schematic and in layout. So either you go into schematic setup or board setup. They will look almost the same. You will have a field here in schematic setup. You go under product, net classes, you push this plus sign, and then it will create another net class. You give it a name, you can give it a color, and if you do it in board setup, you can give it a name and you can give it a default clearance. That default clearance, we're gonna kind of override that later, but that default clearance is what takes effect when you don't have anything else defined. So that would be like a global definition of a clearance if you don't override it with your custom rules. Then you created the net classes, and those are the 6 net classes that we just mentioned, right? And then we have assigning the nets to the net classes, and that's a little bit funky in KiCAD, because we're not really doing it as a property of the net, but we're creating a name filtering, like a pattern, and every net that matches that pattern, you can use wildcard if you want to. You can set that to inherit a net class and whatever properties that comes with that net class. And I think That's very unlike how it's done in many other programs, but I think that was done in order to accommodate for a net to have the properties of more than one net class. I haven't tried that out, but I guess that would work. But yeah, you create the pattern. That's one way. I will explain another way. But you could sit there and type in all the names of your nets and then associate the net class with those nets. And then eventually you will have all your nets in specific net classes. Alternatively, you can go into your schematic, and I will recommend this method because it's a little easier to deal with. You just right-click on the net, and there's a assign net class under the pop-up menu. You can click that one and then choose what net class it comes into. And in that regard, I would recommend you to color the nets, because then you can actually visually see that you got all the nets you wanted into the net class. It's very easy to miss a net if you don't. I don't think there's a net class report or anything like that in the software where you can get like a complete list and then double check that that you got all the nets right. There's a weird funky feature, I don't know, box something. If a net does not have a name, given name, then the only way you can assign the net class, or not the only, then you have to either type in the given name in the layout file or do a place directive on the net and then say this directive gives it a net class. It's a little bit weird. It would be nice if you could just right click and assign the net class anyway, but be aware of that. You cannot, under normal circumstances, just right click the net and assign net class if it doesn't have a name. So now we have assigned or recreated all the net classes. We assigned all the nets to net classes. So we're kind of ready to go into the fun stuff. As I said, you can color the nets, and that's really good for visibility when you're doing it, so you're not missing anything. Then we have to look at how do we create these custom rules, and they have a specific syntax that you have to follow. I've displayed two examples of those here. The rule has a name, it has a constraint description, and then it has a condition. And I'm going to explain it in reverse order because that makes more sense. So you have a condition that has to be met. And since we're doing net class to net class constraints, the condition is one element is having a net class, and that's the name of the net class that you just created. And the second element, this is B, has a net class, and this is another net class that we just created. Remember, we created 6 net classes. We're creating a condition where one element is a member of one net class or has that net class. The other one has another net class. What do we want? What type of constraint do we want? We want a clearance constraint, and we want to set the clearance to a minimum value. So minimum in this case is 1.5 millimeters. That number is taken from the spreadsheet that we created. So you go in there and look. BACN and BACP, those two net classes, their mutual clearance is 1.5 millimeters. So you type in 1.5 millimeters and you give it a name. There's no rules, or there might be rules to the name, but basically you can choose whatever you want to give that, or what name you want to give that rule. Let's take another example. You have one element that is a member of the BDCN class, and you have another member that is a member of the VACP class. That's a condition. So whenever that happens, you set the constraint that the clearance between those two is 2.5 millimeters. Again, that number is taken from the spreadsheet that we created. And then you just give it a name that you find suitable. Good to give it a name that you can recognize what's going on. And then you go into the custom rules on the board setup, and you copy all those rules. You create a rule for every single of those net class to net class constraint, and you copy them in there with the right names and the right numbers. See here, that's here, board setup net custom rules. You type it in here, and if you're in doubt about the syntax or you want some assisting info, there's a syntax help, and I can recommend it. Also have very good examples on how to set up custom rules if you want to, go further. And that's it. You're actually ready to go. You now have set up your board. Your interactive router will make sure that your clearances are kept. If you are doing a zone fill, it will automatically make sure that your clearances are kept. That's it. Let me see if I can actually drag this thing on the screen so we can see it in action. Whoops. Oh my God. Okay, this is a little tricky. Let's say we have a net up here. If you can remember the schematic, this is the fuse. And I remember that this net over here is a member of the same net class. So you can see I can actually drag very close to that net. But if I try to do the same down here, you can see it will actually keep a clearance that is different from the net down here. So now this particular net has at least 2, from you can see here. It has more, but I'm not going to get any closer to the other nets out here. So it works correctly. What you can also see is that if I did a zone fill here, this particular net has created a large clearance here. That is not its own internal clearance, but the clearance to the net that is defined up here. And as such, you have accomplished what you wanted to have net class to net class constraints. Everybody's happy, right? Further information. I took most of my inspiration from Seth's presentation 2 years ago, level up your custom rules. And then also, as I mentioned already, the syntax help also has a lot of very good examples. That's it. Any questions? Whoops.
Yeah, a question. Is it possible if I would have a large clearance, but I have a BGA
A large what?
clearance for the GND, is it possible if I have a BGA package, which is impossible to root with a large clearance, that I ignore in that region the clearance, or have a smaller clearance to root it?
So I don't have the particular experience in doing that. I'm pretty sure if you go into your custom rules, I mean, I'm gonna say what I would try to do. Probably Seth can tell you what to do, but I'm sure that in the custom rules there's something like if it has a specific reference designator, then you can ignore a specific rule, something like that, so that you know that, okay, I can ignore it. Or maybe there's zones where you can create exceptions to rules and stuff like that. I'm pretty sure about that. Yeah.
Somebody here.
Do you want to expand on the matter? Thanks. Other question?
Sure, I have a question. Have you looked into...
Sorry, who's talking?
Oh, hi. Back here. Yeah. Awesome. Thanks for the wonderful demo there. Have you looked into making a script for it? Like, I've been doing custom DRC rules where I just fill out like a spreadsheet, save it to a CSV, and have a Python script that generates the rules for me.
Okay, I didn't get your question, Paul.
The question is, have you looked into sort of like automating the rule generation for this?
I think that would have to be like an external tool for that. I mean, you could write a script or something like that, but no, I don't know of any how to say tool that does it. I mean, if you take other... No, nobody's correcting me here. Okay. I mean, if you take other commercial packages, they usually have like a management system within the CAD suite itself, like a spreadsheet within the program where you type in all those numbers. I omitted a slide because I was not aware if I had enough time, but if I do a large design, like, a huge telecom system with lots of high-speed lanes and lots of power supply and stuff like that, I might have, 30 classes or even more, and then 50 constraints that I want to comply to, and then 12 layers where each layer has a different set of constraints. You get like 20,000 numbers that you're typing into the system. It's dreadful, and you're like, what if I miss something? And I would say there's no good solution. I have never heard of a good solution. I mean, it's dreadful to me, even as a decent pro in this stuff. And I would say KiCAD has done some... They've kind of shaking the conventions, right? And I would say it feels funky, but at the same time, I think there's a need to try things out and see if somebody can come up with a way where can we do this in a right way and an easy way. But I don't know what it would be, but I certainly welcome any suggestions to let's see what can be done.
I guess what I've been doing is I write a Python script that makes the rule, and then I write a script in like Python that can create the rules.
Yeah.
And then I have it just ingest a text file, like a CSV file. So you can draw in your spreadsheet program.
I think that's a perfectly viable way of doing it, especially if you do it multiple times. I mean, this is a very small design, 6 netclass, not a lot, and so yeah. And I just wanted to make sure that I knew how to do it in KiCAD, right? If you're doing a really large design, I would probably also do like a CVS file, and then if you make changes, just rerun a script that extract the constraint information and copy it into the custom rules. That is the right way to do it, I would say.
Your example is very clear, because if you took an example of clearance, clearance, you can see as you go along, you can see the clearance. If I have a length constraint, a length constraint, how does it work when you have a length constraint, which is only when you're running a check a check at the end that it's going to your router's not going to save you on length constraint.
So I don't know with length constraints in KiCAD, because I haven't worked with it in KiCAD. I've worked with it in many other tools, but I don't know if it'll actually come back and tell you that you're violating a specific constraint on the length matching. No, probably not. No. I mean, I never said that all constraints were online. Some of them you would actually have to run a check in order to catch, for sure.
Thank you very much for highlighting this very interesting part of function of the net classes. I was just wondering that all the rules that you entered, they went into DRC, which, from my thinking, would be something that would be done running the DRC on it. But actually, it's like defining rules, and they are obeyed during routing. So that was really interesting for me, and thank you very much for that.
Well, you shouldn't thank me for that. that's on the developers. But yeah, actually, when I did the design, I was like, I probably have to run a DRC check to catch it. And to my surprise as well, I was like, oh, awesome. I mean, it's interactively handling it. It's very nice, yeah.
No. Oh, okay, sorry.
Any other questions? Nope. Well, thank you.